Okay, we're getting into some fun today with formal charges. So formal charges are something that we add on to our Lewis structures. It's a little bit more advanced than just basic Lewis structures, and it helps us assign more correct Lewis structures, because you can come up with lots of different Lewis structures. Some of them are more realistic than others, and formal charges is the system that chemists came up to deal with it. So this is a fake charge, a fictitious charge. It's not an actual charge, it's just a number game that we play. And it's calculated with ignoring electronegativity, so we don't pay attention to electronegativity, at least not in particular to start with. And it's the difference between the number of valence electrons for an atom. For example, chlorine has 7 valence electrons, and the number of electrons that it owns, and bonds are shared equally. So in my mind, the way that bonds work when we're doing Lewis structures is in a bond, there's 1 electron on each side. And the electron that's closer to the atom goes to that atom. So let's say this is 2 chlorines. So this one belongs to this one, and the right one belongs to that one. And if we finished off this structure, we'd have 3 lone pairs on each chlorine. So the number of valence electrons here, we've got 7 valence electrons. We subtract from that the number of non-bonding electrons and half the number of bonding electrons. We've got 6 lone pair electrons on each of our chlorines, and 1/2 of 2 bonds, or bonding electrons, rather. So that would be 7 minus 7. Our formal charge on the chlorines is 0. Some other rules, things that we do with formal charges. 1 and 2 are sort of the same. Any species, charged or uncharged, the sum of the formal charges has to be equal to that. So if it's a neutral molecule, then our formal charge total has to be 0. If we have a -1, like in an ion, or a +1 in an ion, then the sum of our formal charges needs to be the charge of the ion. So for like nitrate, NO3-, the sum of our formal charges needs to equal 1-. And it's better to have small or 0 formal charges on individual atoms. Just like in golf, small number good. And electronegativity does sort of come into play, because if formal charges cannot be avoided, the negative formal charge should reside on the most electronegative atom. They're more likely to draw or pull more electron density. Since the electrons are more likely to be found close to them in any given bond, they are also more likely to have a negative charge. They're more stable with a negative charge than other things. And we will be doing some examples. Formal charges can help us to identify the best skeletal structure for HCN. So we've got in this table 2 different skeletal structures for HCN. We've got carbon as the central atom. We've got nitrogen as the central atom. The number of valence electrons that they each have is listed right below them. So hydrogen has 1 valence electron, carbon 4, nitrogen 5. And we count up the number of non-bonding electrons and the number of bonding electrons with the 1/2 in front. So we're subtracting those numbers away. And we can see what the formal charges are in either of these two structures. So for both of them, for hydrogen, our formal charge is 0 because it just has 1 bond. And 1 bond, it's splitting half of those. And so we just subtract 1 from 1, and we get 0 in both cases. However, when we look at the carbon and the nitrogen, we can see that with carbon in the center, we get a 0 formal charge because there's no lone pairs or non-bonding electrons. It's got 8 electrons in bonds because it has 4 bonds. So 4 minus 4, we get 0. Nitrogen has this lone pair. Wrong button. Nitrogen has this lone pair. So it's got 2 electrons to itself, plus 3 bonds means 3 electrons from that as well. So we end up with a 0 formal charge. If we put nitrogen in the center, then we're just swapping the numbers that we subtracted. So we're subtracting 4 because we've got 4 bonds. We end up with a +1 formal charge. Carbon has the 2 lone pair electrons now, so it subtracts 2, another 3 from the bonds to get a -1 formal charge. So structure A is better because smaller formal charges. So this is an instance where we can avoid formal charges with one of our structures. Sometimes we can't, and so then we have to pick between a couple of options and see which one's better. Let's say that we want to assign formal charges to figure out between each of these 3 resonance structures of N2O which is the most correct. So count up and figure out the formal charges for each atom, 9 things to do, and see which one's probably the best resonance structure based on those formal charges. All right, so for A, the one that I underlined here, this nitrogen normally has 5 valence electrons. It's got 4 electrons from lone pairs. That's these two groups of 2 electrons. And it's got a double bond. A double bond has 4 electrons in it. We take half of those, and subtracting that all out, we get a -1 formal charge on nitrogen. The other way that you could do it, you just cut that bond in half. It's touching 6 electrons. If we do that for the middle nitrogen, if each of these ends of the bonds is an electron, it's got 4 electrons that it's in contact with. It wants to be in contact with 5, and so that means it's going to have a +1. So -1, +1. Oxygen has 4 from lone pairs, 2 from the bonds. It's happy with that situation, so it's got a formal charge of 0. And then we have 0, +1, -1. We've got -2, +1, and +1. So hopefully those are all the numbers that you got. Now, considering the formal charges that we came up with, one of these is clearly the worst. Which one is that?
C.
It's C, because we have formal charges on everything, and we have a -2. These other ones, we don't have any -2s. We have a smaller number of formal charges. So C is definitely not correct. So that leaves us choosing between A and B. The difference between A and B is in A, the left nitrogen has the -1 formal charge. In B, the oxygen has the -1 formal charge. So this is an electronegativity difference scenario. Which is more electronegative, oxygen or nitrogen? It's oxygen. It's closer to fluorine. We could also look it up. So oxygen is more electronegative, happier or more stable with the -1 formal charge. So B is most likely to contribute, or likely to contribute most, rather, to the correct structure of N2O. Questions? Great, we've got some more fun ones. Draw the Lewis structure for diazomethane, CH2N2. Carbon is central. For each resonance structure, assign formal charges to all atoms that have formal charges. I'm going to give you this structure because I'm guessing that you wouldn't come up with it by yourself. There's the skeletal structure. And if we needed to connect everything with one bond, which we do, we would start off with connecting them that way. So give that a shot. I'll be right back. All right, so on the left, I've got the tally of the electrons. And if I remember correctly, there's 2 good resonance structures. So I just went ahead and duplicated that skeleton. Carbon is going to need more electrons. It needs 2 more electrons. There's a couple ways we can do that. We can either add a lone pair, or we can add another bond to that nitrogen. That middle nitrogen, I'm kind of working this backwards a little bit. That middle nitrogen, in the left case, is going to need more electrons. We can do that by increasing the number of bonds with the nitrogen on the right, and then our last 2 electrons would go on that terminal nitrogen. This gets everything a full octet, or in the case of the hydrogens, duets. In the right case here, the middle nitrogen needs more electrons as well. We can place another 2 electrons to get 2 double bonds. And then our last 4 electrons would have to go on that terminal nitrogen. So those should be our 2 good resonance structures. By good, I mean we fulfill our octets. There's other ways you can put it together without full octets, but this is the way that I came up with to get full octets for everything. And then we want to check formal charges. Our hydrogens all have 1 bond. They have formal charges of 0. Carbon, and this left one, if we cut all these bonds in half, it would have 5 electrons touching it, the 2 from the lone pairs, 1 from each of the bonds. It would like to have 4, and so that puts a -1 onto carbon. Our nitrogen in the middle has contact with 4 electrons. It would like to have contact with 5. So that's going to be a +1. It's 1 short of the number of electrons that it would like to have. The terminal nitrogen has a formal charge of 0. It's got the 2 in the lone pair, and it's got half of the 6 in the triple bond, which is 3. So 2 + 3, that's 5. That's exactly how much nitrogen wants. And then in our right resonance structure, carbon has the 0 formal charge. Our middle nitrogen has the +1 still because it only has 4 bonds. And then the right nitrogen has 1 more electron than it would like to have contact with. So we need to consider which of these, well, we don't need to consider actually. We just need to assign charges. If we wanted to, we could guess about which one has the greater contribution to the overall structure. I would say that it's this right one because nitrogen is more electronegative than carbon. Questions about those resonance structures? Okay, we also have some exceptions to the octet rule. First, we're going to talk about odd electron species. Odd like 1, 3, 5, etc., not as in they're quirky. So free radicals are one such instance of odd electron species. The radical part means that they have a single electron that's just by itself. Rather than having it in a lone pair, they've just got a solo electron. Radicals do exist, and they will have odd numbers of electrons. If you have an odd number of electrons, you can't have octets for every atom. It's just the way that the math works out. Free radicals tend to be unstable and reactive. So they're generally not going to stick around for a super long amount of time. They might be produced. They're bombarded with UV radiation in the upper atmosphere. That causes them to break apart into something, or they absorb a photon. They turn into a free radical species. Then they go hit something, turn back into their normal state, and then the cycle continues. We can draw a Lewis structure for NO. Nitrogen's 5 electrons, oxygen is 6 electrons. That means we will have 11 electrons. There's 2 of them. 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11. That doesn't fulfill octets for nitrogen. At least it doesn't come close enough, so I'll add a pair in for a double bond. Now nitrogen has 7 electrons on it. Oxygen has its 8. The other way that we could draw this is if we swapped one of those electrons over to be on the nitrogen. So these are our 2 options for the free radical NO. If we look at the formal charges, this top one that I drew out first, our formal charges are 0. The nitrogen has contact with 5 electrons, 3 in the form of the lone pair in the radical, and 2 from the double bond. The oxygen has 4 from lone pairs and 2 from the double bond for 6. That's exactly how many it wants. In the lower structure, we swapped the number of electrons. So nitrogen's going to have a -1, oxygen's going to have a +1. So that upper species should be correct. And that's just because of the formal charges. If we didn't have a formal charge system, we wouldn't know how to pick the better of the 2. Which of these, you don't need to actually draw them out, which of these molecules would you expect to be a free radical? The reason that you don't need to draw these out is a free radical is going to have an odd number of electrons. It has to have an odd number of electrons, otherwise you wouldn't be able to end up with just 1 electron by itself. You're probably never going to have 2 radicals in the same species. That would be extra unstable. And so what we're looking for is the total number of electrons. And which of these has an odd number? So CO, carbon monoxide, has 10. That's an even number. And we've got, struggling at math, 16 in CO2. N2O, nitrogen has 5 each, but we've got 2 of them. This one also has 16. And then for the last one, chlorine, has 7, and oxygen has 6. So that would be 13 electrons. So that is the one we would expect to be a free radical, because it has an odd number of electrons. We can also have incomplete octets. Boron is the poster child for incomplete octets. Boron is a bit of an odd child. It has compounds where it has 6 electrons, and those are stable. If we look at the Lewis structure for boron trifluoride, boron's going to be in the middle for symmetry reasons. And that's what our structure will look like. We could add in a double bond from any of these fluorines, right? And then we would have, let's say, a double bond with that left fluorine. It doesn't really matter which one we look at. If we check the formal charges of such a system, we'll find that each of our other fluorines has a formal charge of 0. Our left fluorine is going to have a +1, 7 minus 4 plus 1/2 of 4, based on that formula. So it's in contact with 6 electrons. And our boron in the middle, boron normally has 3 valence electrons, and it'll be in contact with 4. So that would give it a -1. If we don't have those, then we've got zeros for our formal charges on all of our fluorines, and our boron also has a 0 for its formal charge. So formal charges help us predict that boron is happy with just 3. It does tend to react in a way that completes the octet on boron. So the boron will form another bond after reacting or through reacting, but it's relatively stable as boron trifluoride. Another odd exception is expanded octets. This one's odd in the quirky way, not in the numbers between even numbers. So elements that are in period 3 and higher, so sodium and things that are below it on the periodic table, things that are bigger than sodium, or smaller in the case of things to the right of it. These can exhibit expanded octets. So more than 8 electrons. And the reason that they can form things that we call expanded octets are because they have access to d orbitals. Or the way that I've described it to my 3A students, they have extra pockets or they can hide the electrons. Since our d orbitals are going to be empty when we're in that n equals 3, and if we're further down the periodic table than that, we'll have our 4d or our 5d, possibly even our f orbitals, and those are typically going to be empty because we fill those in later. All right, Lewis structures. Arsenic, being under nitrogen in the pnictogen category, has 5 valence electrons, and each of our fluorines is going to have 7. That'll end up giving us this sort of a structure. Each of our fluorines, having access only to s and p orbitals, has an octet. Arsenic has 10 electrons on it because of those 5 bonds. In SF6, sulfur hexafluoride, sulfur, being right under oxygen, also has 6 valence electrons. And the fluorines each have 7. You don't really need to worry about copying down these structures. I'm drawing them out real quick just to save us time. So each of our fluorines have formal charges of 0 in both of these cases. And our sulfur and arsenic also have formal charges of 0, despite them having 10 and 12 electrons. So expanded octets, we're only going to have expanded octets on things that are period 3 or higher. That is, the period number is higher, so period 4, 5, 6, 7. Period 2 elements are never going to have expanded octets because they don't have access to d orbitals. This is our skeletal structure for sulfuric acid H2SO4. We are going to have 32 electrons in both cases, minus 2, 4, 6 bonds. That'll leave us with 20 electrons to place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we just gave all of those 20 electrons to our oxygens as lone pairs. This on the left is if we don't have expanded octets with sulfur. So what we're going to be looking at here is the formal charges. Our hydrogens have zeros. Our oxygens that are between the hydrogens and the sulfur have zeros. Our oxygens up top have a -1. We've got the 6 that our oxygen wants from the lone pairs plus 1 more from the bond. So that's our extra. The bottom one is also going to have a -1 formal charge. The sulfur in the middle, being only in contact with the 4 bonds, gets 4 electrons. It wants 6, so it carries a +2 formal charge. What could we do differently if we can expand our octet on the sulfur? So if our sulfur can take on extra electrons, our oxygens here on these side ones between the sulfur and the hydrogen, these ones are happy. They've got a 0 for their formal charge. So we're probably not going to do anything with them. We'll leave those as zeros. But our top and bottom oxygens have -1 formal charges. We can reduce that formal charge by sharing a lone pair in the form of a double bond with our sulfur in the middle. So now instead of having a -1 formal charge, we've got 2 lone pairs, that's 4 electrons. Another 2 in the double bond, that's 6 electrons for our formal charge calculation. That's what they want. And so we have formal charges of 0 for everything. So H2SO4 with those double bonds is better from a formal charges perspective. And that's only possible because we can use an expanded octet. Questions? All right, try writing a Lewis structure for xenon tetrafluoride. You can also try writing a Lewis structure for phosphoric acid. it's going to look similar to that sulfuric acid one that we saw in the previous slide. The hydrogens will be bonded to oxygens. What do we have for xenon tetrafluoride? Does anyone have a finished structure? So if we put this together without knowledge of expanded octets, we would run into a problem because we connect everything together. Our xenon is in the middle, our fluorines are on the outside. We needed 8 electrons just to get everything connected. That's the 4 bonds that we put in. That leaves us with 28 remaining electrons. I put 24 of them out here with red dots by putting 6 on each fluorine. Since there's 4 fluorines, that's a total of 24 electrons. That leaves us with 4 electrons left over. But everything has a full octet. So this is one of those places where expanded octets comes in handy. If you find fluorine on the periodic table, it's one of our noble gases. It's on the bigger side of noble gases. And it can have access, it has access to d orbitals. And so we can give it 4 more electrons. Because xenon can expand its octet. Fluorine wouldn't be able to do that because it's in period 2. It doesn't have access to d orbitals. And when we do this, if we do our formal charge calculations, our fluorine has 6 from lone pairs, 1 from the bond. It's got 7. It's happy. Fluorines all have their contact with 7 electrons. Our xenon in the middle gets 4 from the bonds and 4 from the lone pairs, so it has 8. It also has a formal charge of 0. Our Lewis structure for phosphoric acid takes up an unfortunate amount of space. So it might look something like that for our skeletal structure. We've got 3 hydrogens, 4 oxygens. That's going to be 24 electrons. And we've got a phosphorus that'll have 5 valence electrons. So 24 plus 8, 32 valence electrons. To get everything connected, we used 1, 2, 3, 4, 5, 6, 7 bonds. 2 electrons each, 14 bonding electrons. We have 18 remaining electrons. We can place those on our oxygens. If we look at our formal charges, oxygen likes to have 2 bonds because it gets a formal charge of 0. So we've got our 4 in the lone pairs, 1 from each of the bonds, total of 6. So for formal charges, these blue circles, those are all zeros. The oxygen up top has 6 electrons from lone pairs, 1 from the bond. It's got 1 more than it wants. It's in contact with 7 electrons instead of 6. And the phosphorus in the middle has to take on this extra charge, or the opposite of it. It would like to have contact with 5 electrons, but since it only has 4 bonds, is only in contact with 4 electrons. That's the way that my brain thinks of it, at least. Just like with our sulfuric acid, there's a way that we can reduce our formal charges, and that's by throwing one of these lone pairs in as a double bond. So now our top oxygen, the one that's not bonded twice, is bonded twice. It's got 2 bonds, that's 2 electrons. And for lone pair electrons, it's got its formal charge of 0. Our phosphorus in the middle has 5 bonds. It's got contact with 5 electrons. It's happy. We could only do that by expanding its octet. Questions? Okay, let's do something with numbers now. Bond energies and bond lengths. This is kind of building off of a similar concept to Hess's law, where we were adding up the standard enthalpy of formation, the delta H with the degree sign F. These things, the stuff we were doing with those, it's kind of similar to what we were doing with those for bond energy. So we can also use individual bond energies, the energy associated with one bond and how much it takes to break it, to calculate or estimate an enthalpy change. So our bond energy is the energy to break 1 mole of a bond in the gas phase. It's always going to be a positive number. I don't know why I drew an arrow. It's always going to be positive. And a bond is stronger if it takes more energy to break. If you have stronger bonds, then they'll tend to be more stable because they're harder to break. They also tend to be less reactive, again, because it's harder to break the bond. So for example, the bond between hydrogen and chlorine in HCl, to break a mole of that bond is about 431 kilojoules. We have no frame of reference for what that number means. It's like a little bit on the higher side for stuff that we'll be looking at today. So we have to put in 431 kilojoules to break 1 mole of HCl. You can calculate the bond energy for like specific scenarios, like for the HCl. You can get a bunch of HCl as a gas, and you could shoot a bunch of energy at it and figure out that you've broken all the bonds. And you can calculate that delta H for that exact specific scenario. But it's a little bit harder to do that in some cases, especially if there's multiple bonds. And so average bond energy is very helpful. So the average bond energy is just an average of bond energies. So we take a bunch of different compounds that have like a specific bond that you can break. You shoot a bunch of electrons or something at them to break those bonds. And you figure out approximately how much energy it takes. Approximate energy to break that bond. This might be like if you went around to all of the fast food chains in the area and got a large soda, and then you calculate out the average cost of a large soda. You could say, hey, it costs $1.79 to get a large soda at a fast food chain. You might walk into like a Chick-fil-A and maybe it costs more there, I have no clue. But it might be $2.09 for a large soda. That's expected because you're using an average. So it's 30 cents more. Somewhere else, though, it might be 30 cents less, or it might be 20 cents less. So there's a little bit of plus or minus to our average bond energies, just like there's a little bit of plus or minus like to gas prices. On average, there's some value, but there's going to be some that are higher, some that are lower. It's just a way that we can estimate. So for example, a carbon-hydrogen bond, this is typically how we'll look at them, a bond between two different atoms. It varies depending on the molecule. So in methane, breaking one of those bonds takes an input of 438 kilojoules. If it's in F3CH, it's 446, so it takes a little more energy. If it's in a compound with bromine instead, it's 402, and it's 401 if you have chlorine as those other groups. So we can average that bond energy out to 414 kilojoules and then use it to estimate in other compounds. So that's why we're using averages, is because it lets us make an estimate. If you have double and triple bonds, those are going to be higher bond energies. They're stronger bonds. All right, we are going to be using this table for a couple of examples. So you might want to take a picture, unless you just happen to have the book with you, in which case you could also just look up this table in the book. So this table, which if you need it on an exam, I'll give you these values. This shows us a bunch of different bonds that we might see, and it shows the bond energy for that bond. So for example, the hydrogen-carbon bond with its single bond is about 414 kilojoules per mole to break. A carbon-carbon single bond is about 347 kilojoules. The carbon-carbon double bond is 611 kilojoules. A bigger number because it's a double bond, it's a stronger bond, it takes more energy to break. And lots of other examples. So we can use average bond energies to estimate our enthalpy changes. Some things that we need to keep in mind is that breaking bonds is endothermic. We have to put in energy to break bonds. And that might seem intuitive. Bonds forming is exothermic. Energy is released. One way that I might, or you might think about it, is the atoms have to settle down. Kind of like that wild person you might know from high school who got married, maybe? I don't know. That's just an example of something that happens sometimes, right? Somebody's really crazy in high school and then they really settle down and get married. And then they're just like a normal person. Probably the real reason is because it's more stable to be in a bond, and stability is lower energy. So what we're going to do in these calculations, you can use this formula. The sigma letters over here mean that we're summing or adding up all of the energy of the bonds broken. And we're going to add to that the negative value, that's the bonds being formed. We've got a couple of examples. All right, so here's one with a visual. If we start with methane and chlorine gas, and we want to calculate the change in enthalpy to form HCl and chloromethane, we have to break a couple of bonds. So we break a CH bond, we break a Cl-Cl bond. In our table that we looked at earlier, the CH bond is 414 kilojoules per mole. So we have to put in 414 kilojoules per mole to break that bond. We also have a Cl-Cl bond, and that is 243 kilojoules per mole. So we have to put in that energy to break those bonds. That's why we're going up on this enthalpy chart. We're increasing energy, putting energy in. And then we get to make a CCl bond. That's going to be in the left column at the very bottom. That has a value of 339. And it's a negative because we're forming the bond. Our HCl bond is also in there. It's more towards the top. And that's going to be a minus 431 kilojoules per mole for all those green numbers. And you can probably see 431 is pretty similar to 414. 339 is bigger than 243. So you can see hopefully we're overall lowering the energy. And that's what this delta H of reaction here is. It would be the difference of whatever that is. Whoever we is, they often say energy is stored in chemical bonds. If you break a chemical bond, that takes energy. Energy-rich compounds, like TNT, have weak bonds. Weak bonds are easy to break. So it doesn't take a lot of energy to break the bond, and then when they form bonds, they settle down a lot. They release a lot of energy. Those two things kind of happen at the same time. But it's the forming part of the chemical bonds that releases energy. All right, scooting off to do another example. I know that there's another calculation one in here that I'd like to get to before the end of class. Okay, the reaction between hydrogen and oxygen as gas to form water is highly exothermic. Which statement is true of the energies of the bonds that break and form during the reaction? Is it that the energy needed to break the required bonds is greater than the energy released? Is it less than the energy released? Or is it about the same as the energy released? Without doing any calculations, what do we think? B. Why is it B?
Because it would be negative. Because in order to break it's positive, and because there's less of the energy release, the answer would be negative or less.
Yeah, so the key words in the question are that it's highly exothermic. That means lots of energy released. It's actually explosive. So the energy required to break the bonds, that energy is positive. That's an input. And the energy released when new bonds formed is negative. That's energy lost by the electrons or by the atoms as they settle down to form bonds. So what we're saying is that we've got a very negative number for our enthalpy, which corresponds with highly exothermic. All right, a potential future fuel, I don't know if this is still accurate, is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. To save us time, and also just to show you how to do it, I'm going to assume that we know how to do combustion reactions and balancing for them. So methanol is CH3OH. A combustion reaction typically involves the reaction with oxygen as O2. And if it's carbon, hydrogen, and oxygen only, for our primary reactant, then we make CO2, and we also make H2O. We're assuming complete combustion. So that's the basic skeleton, and then we get to balance it. For carbon, we've got one on each side. We're good on carbon. We balance hydrogen next. We've got 4 on the left side, 2 on the right side. We can get those to balance, add a 2 in front of our H2O. And then the last thing that we balance is oxygen. We're balancing oxygen last because we have O2 by itself, so we can change that freely without affecting anything else. At present, we have 3 oxygens on the left side. We've got 2 plus 2 times 1 for a total of 4 on the right side. So we need a coefficient in front of our O2 that gets us up to a total of 4. In this case, that's going to be 3/2. That gets things balanced out, but we have a coefficient with a fraction in it, and so we multiply everything by 2. So there's our balanced equation for the combustion of methanol. And if you can believe it, that's the fast part. Or at least to me, that's the fast part. So now the other thing that we get to do is calculate the energy to break the bonds, calculate the energy to form the bonds. So we're going to break everything on the left side. And form the right side. Our Lewis structures, the exact details don't really matter. We just kind of want the shapes so that we can see what the bonds are. We do need to know if there's double bonds or triple bonds anywhere. So in that way, it's important. So we're going to have 2 of those methanols. We're going to have 3 oxygens. Our O2 Lewis structure has a double bond in it. So that's the left side. And then on the right side, we've got 2 CO2s. Carbon dioxide has 2 double bonds. That makes it quite stable. And we also have 4 waters. And then we count up how many of each bond type we have. So in each of our methanols, we've got 3 of these CH bonds. So we've got 6 CH bonds. We also have 2 times 1 each CO and 2 OH, or as probably shows up in our table, HO. And we also have 3 oxygen double bonded to oxygens. Questions about any of that? If I had more space, I would have written more things out. I used a little more space than I did going through it last night. And then on the product side, we've got 2 times 2 carbon double bonded to oxygens. And we've got 4 times 2. We'll keep writing it as OH, just because that's how it showed up earlier. Questions about the bond counts? No questions, hopefully. Okay, and then we look at our table and find our values for each of these. So for CH or HC, 414. For CO, that's lower on the far left column. 360 for our OH. 464. And our O2 in the middle of the middle column. 498. And on our product side, our carbon double bonded to oxygen is 799. That's a little, there's an asterisk below the far left column for that one. And for our OH, again, it's 464. So what does this look like going into a calculator? We've got 6 times 414 plus 2 times 360 plus 2 times 464 plus 3 times 498. That's for our reactant side. So add all of that together. That's the amount of energy we have to put in to break the bonds. On the product side, we've got 4 times basically 800 plus 8 times 464, and this value is negative. That's the energy released. And let me grab my calculator, plug this in real quick to get an answer. So the left side, 5,626 kilojoules per mole, plus the negative of the other side, 6,908 kilojoules per mole. So our enthalpy of combustion, we could estimate as 1,282 kilojoules per mole. So there's a lot of steps. I don't think it's especially crazy steps. It's just a lot of steps. I would say expect one of these questions on exam 4.